Hmm. So, in the last couple of classes, we've been talking about embodied AI systems and they being receiving sensory stimuli from the real world, activating sections of their knowledge representation or their knowledge graphs, and accordingly designing plans for their activity, right? So now, whatever we have discussed so far comes under classical planning because it does not talk about time as a very integral part of a planning algorithm. Right? It just talks about an order of activities, what to do, and in what sequence. But it doesn't talk about a very important resource, which is time. And if you remember in the earlier classes, also, I was talking about the concept of objective time and subjective time, which is a very integral part of when you're trying to design a social system or a socially embodied system. The concept of time, both in its objective and subjective flavors, is important. Similarly, when you're trying to design an algorithm, a planning algorithm for actually functioning in the real world where resources are constrained, then it is important to keep track of the time, right? Like, for example, when in operating systems we talk about job scheduling, then CPU time is very important. You cannot have one process hogging onto the entire CPU forever, right? You have to make sure that processes keep coming and execution keeps happening at a pretty fair enough rate so that there is no live log, deadlock, starvation kind of processes happening. Deadlock is when no process, each process is waiting for the other one to complete, and it's just a chain of processes waiting, right? And no one can move forward. And live lock is it's not moving forward, but nothing effective is happening. Right. Like, for example, there is a narrow passage and you have, and say you and I are trying to get through it. We're just saying you first and you first. Okay. We just keep doing that. We take a step, but nothing effective is happening. So we are in an active situation, but nothing is happening. Similarly, in starvation, it is like a very high priority process or a very large process is hogging onto the entire resource, so that the smaller processes or the low priority processes are constantly waiting for resources to be allocated. So, given these kinds of scenarios, it is not only in operating systems, it is in our everyday systems also. In the way you and I function, the way we want our AI systems to function, resources are constrained, right? So we have to make effective use of it, for which time is very important. So when we come into planning in the real world, it's not just sensory stimuli, but the time within which we process it, the time, the turnaround time, the time in which we actually execute it, the time in which we respond to it is very essential. And if you remember in one of the earlier classes also, I had talked about a window within which you collect the sensory stimuli for processing. So there also you see a time gap is very essential, right? A time within which you collect a packet of information for further processing. Okay, so in this particular chapter, I think this is chapter 11 of Norway. Okay, so I have done a bit of chapter 11 and a little bit of chapter 13. Okay, a little bit, nothing very significant. So, yeah. So now when we talk about planning in the real world, there are essentially two phases. One is a planning phase, which is you select what action to do, and then your scheduling phase. Scheduling phase meaning in at what time do you want something to be done, or within what time. So here it is at what time and within what time. So the time at which it's supposed to start and the duration. And alongside that, there are a few other things also. There is an algorithm called the critical path method that helps us decide an effective scheduling procedure. Okay, so you have a number of, let me show you this. Wait. So let's take this example. Here we are trying to build two cars. Okay, so the different steps are you have to add an engine, you have to add a wheel, you have to inspect it, and you have to finish it. Okay, so these are the different steps, and we are trying to build two cars. So the concepts which are very important over here is the earliest start time. At what time do you start? The latest, the last start time means the time within which you absolutely have to start. Okay, means the time at which you can start and the time at which you absolutely have to start. So it's the earliest start time, the latest start time, and the difference between the two gives you a bit of slack. Slack meaning, like for example, I give you an assignment, you can start doing it right now, or you can decide to do it 5 hours later. So you have a slack of 5 hours. But if you delay it more than 5 hours, then the assignment will not be complete. Right. So you have an earlier starting time, which is right now. You have a latest starting time, which is say within 5 hours, and the slack is 5 or 5 hours. Okay. So if we have these concepts pretty clear, then we can actually identify a process or a mechanism through which we can order our activities in such a way so that it gets done within the required time. Okay, so now if we look at this, here we have, oops, yeah. So here you see the first time that you're seeing over here, this is the earliest start time, okay, 0. And then 15 is the duration within which it has to be done. Okay, sorry, not the duration, sorry, it is the latest start time. So we start at 0, 0, add engine, the earliest start time is 0 for both of them, add engine 1, add engine 2, the start time is 0. But the latest start time for add engine 1 is 15. So within 15 units, you absolutely have to start it. Otherwise, it won't be effective anymore. And for add engine 2, it's 0. So now these values that you get for early start time, last start time, these need not be random all the time. These could be a function of your experiences. This could be a function of your current energy factor, right? Like for example, if you are not feeling well, then starting an assignment 5 hours later may not be a very good idea because you actually may not be able to complete it. So why not start taking small steps from now? Okay, so you have a choice over there, right? And what have you decided this? Why have you decided this kind of a slack? It is because you know how you work when you are unwell. You know what your energy conditions are. You know what your limitations are. Okay, and it is a subject of your. It's a function of your past history activity. Okay, so it's not that you do it randomly. You have a certain episodic memory that is leading to you taking a decision on what is going to be your last start time. Okay, so similarly over here, given this car manufacturing company, they know that these kinds of slack times are allowable, not beyond that. Fine. So now the 30 and the 60 that you see the numbers below, these are durations. Okay. So if I assume that the add engine 1 starts at 0, given a duration of 30, add wheels 1 will start at 30. Similarly, if it starts at 15, the next add wheels 1, the last start time for it should be 45. 15 plus 30, 45. So this is how you move on. And at 85, it all ends. So now if you convert this into a graph, this entire flow chart, if you convert it into a graph, this is what you see, the diagram at the bottom. The gray sections you see, these are your slack times, the times within which you can postpone things a little bit here and there, but you absolutely have to fit your activity within that gray slot. Okay, so in the critical path method, what we do is you identify these different time slots, early start time, last start time, approximate durations, and you design this entire graph and you look at the longest path that is there from start to finish. The longest path is going to give you the critical path. Why? Because it will not go beyond this. You know that given whatever largest slack times you have used, the entire duration of that activity or the time that it will take to complete that activity will not go beyond that longest time. So this is the critical path method. Now, in sync with this, you can also add resource constraints. Okay, so over here we are assuming that all resources are available. But resources are of two kinds. One is consumable and another one is reusable. Consumable meaning once you use it, it's finished, it's exhausted. And reusable meaning you can keep recalling it again. You can recall that function, you can reuse a certain module. Okay, so in sync with the critical path method, if you keep track of the resources that you have used, how many resources you have used, how many you have left, then you can accordingly schedule the entire uh, the steps of these processes that you are trying to complete. Okay, because unless you keep a track of the number of resources that are available to you, time cannot be the only thing. Right. So in an effective critical path method, it's just not time, but also resources that you have to take into consideration. Okay. Here there is an example also here. You see, here they have added resources, which is engine, wheel stations, and inspectors. Inspectors is the reusable component, and wheel stations and engine hoists are the consumable sectors. So they have redesigned the critical path method, keeping in track of which engine, like when to start what, based on resource constraints. Okay. So the first one was considering only time and assuming all resources are available at all times. But this is a more figure 11.3. This is a little more realistic in the sense that it takes into consideration that resources may get exhausted or not all processes have to be concurrent. Like if you are fixing the wheels of one car, your manufacturing unit may not have the capacity to fix the wheels of another car. Okay, so ideally they can run concurrently, but given the resources available, you have to make sure which one you want to do first. Now, there are many ways you can choose which one to do first. It could be based on market requirement, it could be based, that could be a priority factor, market requirement, or it could be just need of the situation. You need to do something before the other, or it could be like a larger process needs to be finished before the smaller one comes, or you choose a smaller process to finish before the larger process. Okay, so given the kind of use case you are dealing with, you decide how to prioritize processes. Okay, if you can do them concurrently, very well. Depending upon the setup you have, you can. But if you have resource constraints, then maybe a serializable schedule would be an effective one. Okay, or you can do an ensemble of both. Some processes are serial while some are concurrent. Okay, depending upon the resources you have, depending upon the constraints you have, depending upon your need. Okay, depending upon your use case. So there is no hard and fast rule that if this is the situation, then exactly this has to be the planning strategy. It all depends upon your use case and what you have available. Okay. Hmm. So now, when we talk about critical path method, another, just like I told you about the shortest job first, or the first come first serve process, or maybe you give all processes an equal time quantum uh, in a circular fashion so that they keep executing a bit by, excuse me, bit by bit, like a round robin scheduling algorithm. Another algorithm available is the minimum slack algorithm. Minimum slack algorithm is what? For every task, you calculate the slack, which is the latest start time minus the earlier start time. And then you sort the tasks in ascending order of the slack time. And then the one which is the smallest, you start that. And when once that finishes, you re-evaluate the slack of all the remaining processes. Again, you sort them and again you go forward. Okay, so at every point in time, you are calculating the current slack scenario of all the processes and then you're taking a decision. And the one that has the minimum slack, that is the one you are choosing first. Okay. So now certain advantages to this is you can include processes within a list. You can deal with periodic, aperiodic processes. All of that is fine. And you are always trying to look at the minimum slack time. So you are very concerned about deadlines. Okay, depending upon system resource utilization. But the disadvantage of it is the computing time. You have to evaluate the slack after every process ends, and you have to sort the processes after one process ends. So a sorting algorithm, the evaluation of slack is always going to be time consuming. It won't be a very effective procedure. So, and if you have sporadic processes, meaning processes that don't come in a continuous sequence, then also it could become ineffective because you are waiting for a long time. Okay. And priority inversion is difficult. Priority inversion is like dynamic priority assignment. Let me give you an example. Say you have something like a large process and a small process. So now say this has executed 80% and this hasn't even started. Okay. And saying I'm doing a shortest job first algorithm. So now given this situation, the shortest job first could be this one. Okay, given this is the time that it is left and this is the time that it needs. And maybe this one, say A and B, A is less than B. Okay, and since A is the shortest job, you give it preference to do, to execute. But now, say for example, another process comes in which has time gap. A finishes, it moves out of the system, and now a new process comes with time stamps, which is or a duration requirement, which is of the order of A. So again, B is waiting, and another A finishes, and this can keep on happening. Okay, so what happens is B, it keeps on waiting constantly for the shortest jobs to finish. So at a certain point in time, it might be wise to actually invert the priority. Given this larger process, which is B, since it has been waiting for a very long time, you allow it to execute. You give it priority to execute before all the other A order A processes. You allow B to execute and move out of the system. Okay, so you have to take that strategic decision that if after say a time duration of T, if longer processes are constantly in that starvation mode where they're constantly waiting for a resource, then why not invert their priority? Allow these processes to move out of the system, and then you again go back to the classical shortest job first algorithm. Okay, so now when you have a minimum slack algorithm, assigning these kinds of priorities could become difficult, but it is not impossible. You can definitely revamp a minimum slack algorithm to include priority revision inversion. You can definitely do that. If like shortest job first, minimum slack is has the same flavor as the shortest job first algorithm, so if priority inversion can be included in a shortest job, then why not in minimum slack? Okay. In classical algorithms, they will not allow you to do that. But in an effective real world adaptive algorithm, why not? Okay. And this time window within which you are going to decide that when you are going to do priority inversion could be adaptive in nature. It doesn't have to be fixed. It doesn't have to be that within the last 10 minutes, which long processes are not getting executed but have been waiting for a long time, let me allow them. You need not keep that time fixed. It could be adaptable. Okay, depending upon the dynamics of the system, you can make T adaptable. Okay, so there are many ways you can experiment with time given the resource constraints and the need of the situation. You can actually modify your algorithms. You can make an adaptive. So any thoughts on how you would like to make uh, a priority inversion strategy adaptive? Any factor you think would be essential? Any parameter you think would help in dealing with or in creating an adaptive priority inversion strategy within the minimum slack algorithm or shortest job first algorithm? Any thoughts? Mhm. One thing is keeping it fixed, like after every 10 minutes you check, or after 20 minutes you check. Okay, or it could be based upon historical data, the way you train your AI system. right? Like, say, given a history of these kinds of processes, an effective turnaround time within which a priority inversion would be effective would be, say, 10 milliseconds or 20 milliseconds. So you do a statistical analysis of historic records of processes execution. That can also be a factor on which you decide how to make it adaptive. Or you can also look at system activity. When a system is idle, okay, or you can think about, I talked about historic processes. You can also think about, say, for example, keeping bursts. Okay, within a fixed time slot, you keep bursts of priority inversion. Okay, that is also something that you can think about. So, all of that, you have a lot of freedom when it comes to designing these kinds of algorithms. You have a vanilla flavor, which is like a vanilla algorithm, which is minimum slack or shortest job first or round robin. And then you can make it your own depending upon the situation. Okay, so deadlock, live lock, starvation, I just told you. So these are very important when it comes to planning. You cannot allow processes to hog onto the entire resource set that is available. You cannot allow the dependency to work in such a way that one process keeps on waiting for the second one in a circular fashion. Okay, so that none of the processes are moving. You have to make sure that there are no bottlenecks within the resource execution, within that process execution, so that it's just because of that bottleneck, the processes are in live lock. No effective process is going forward or no activity is happening. And you should also ensure that there is no starvation happening, meaning some processes are all forever waiting for something else to finish, like a priority algorithm gone wrong. Okay, so that is why priority inversion and these kinds of techniques, or an adaptive priority strategy, or incrementally priority, incrementing the priority values or decrementing priority values, these kinds of strategies can help. Okay, so now we come to hierarchical planning. In hierarchical planning, what we do is, given a particular problem, you try to break it down into goals and sub-goals. Okay. A top-down mechanism of decomposing a given problem into goals and sub-goals. Okay. So say, for example, I ask you to bake a cake. So the goal is to bake a cake. And what are the sub-goals? You have to heat the oven. You have to measure the dry ingredients. You have to measure the wet ingredients. You have to mix them. You have to maybe keep them for some time. And then you put it in the oven. You have to butter the tray in which you're going to make the cake. So you have these different sub-goals, right? And you can keep decomposing these sub goals till its very atomic functions. Okay, you can keep on doing it. So these atomic functions are primitive functions, meaning you can no longer decompose them. An example of a primitive function could be lift a spoon. Okay, or move this from here to there, from A to B, or pour sugar into the bowl. There is nothing that you can decompose about it, right? So you break down an activity, you have a large goal, you break it down into sub goals, and you keep on doing this till you come to a list of primitive operations. So here what you have is a tree, a hierarchical structure of all the processes that you need to do in order to get to achieve a goal. Okay, so how do we now go about it? So it's now given the kind of problem you have to see whether these subgoals can be executed concurrently or they have to be in serial order. Okay, so that is going to kind of define or give a certain environment within which you're going to operate. If they're going to be concurrent, then the treatment is going to be in one fashion. But if it is going to be serial, then it's going to be in another fashion. So the tree, the hierarchical plan that you're going to follow has to be drawn in that particular way so that it is evident that which sub goals can be achieved concurrently and which sub goals have to be achieved in serial fashion. Okay, and within these sub goals, these primitive operations that we have, you can actually have options of primitive options, primitive actions. Okay, yeah. So, say for example, there is not just one way of doing one activity. You have a sub goal X, and you have list of steps, and say these are different options through which you can actually execute X. So out of these options, now you can choose which one to do. If all of them are absolutely essential, there is nothing that you can do about it. But if there is a choice, then given your resource constraints, given your energy constraints, given your time constraints, you can decide which option to choose. Okay, so now over here, a certain definition which is very important is the reaching state. The reaching state is given a current state S and a sequence of activities, say H1 and H2, we have to make sure that given the current state and the sequence of activities, whether you are going to reach the goal state or not. So the reach state is given state S and a sequence of activities, you try to identify all the states that are reachable given the sequence of activities from S. So the sequence of states that you guess, and if the intersection with the goal state is not empty, that means you have a reachable possibility given S if you follow the sequence H1, H2. H1, H2 sequence meaning sequence of activities, right? If you remember when we were drawing the graphs in the last class about the activity graphs, we had states and activities, planning graphs, right? It's same over here. So you are standing at one state, you have a sequence of activities, you look at all the states that are reachable given S. So if this this set of reachable states intersects with the goal state or the goal states, then you have a reachable set or a reach set. And when you have a reach set, you are assured that from this particular state, given H1, H2, you can actually arrive at a goal. Okay, so what we are first doing, you are given an activity, you are trying to you're decomposing it into sub goals. From sub goals, you are arriving at primitive functions. Primitive functions could be absolutely fixed in order, fixed in sequence. They could be concurrent. They could be choices or options, depending upon the use case that you have. So now, given all of that, you look in order to identify whether you are moving in the right direction of execution, you identify reach states. Okay, you have an activity plan and you have a certain state that you have achieved. You look at the reach state. And if you see that the reach state is actually coinciding or intersecting with the goal state, you know that you are in the right direction. So now when you have a hierarchical graph like this, can you talk to me about some algorithms that you think would be very effective in order to identify a goal state or a reach state? Goal sets and reach sets? Any algorithm? You have definitely done this. Remember, you're planning something. Okay. So when you're planning something, what do you do that helps you move closer towards your goal? What is it that you do? See, when you're playing a game of chess, you are in one state, you have a possibility of sequence of actions. How do you choose which action to take? What do you do? You have a hierarchical graph over there, isn't it? Don't you look ahead a few steps? Yes? say you look ahead a few steps, isn't it? You look ahead 2 steps or you look ahead 3 steps to identify the next few states that are possible. So, a look ahead strategy where you keep track of how many steps or how many action sequences you are looking ahead could be a way to help you plan effectively. It is not that you have to just think about the current state, but you look forward and you do counterfactual planning. You try to simulate a virtual environment where if you took this decision, what would happen? If you take another set of sequences, what will happen? And then you decide what you want to do. So, a look ahead kind of a strategy where you look forward, or given the current state, you move forward by 3 states or you move forward by 4 states, given the kind of memory capacity and processing capacity you have, you can actually identify effectively what plan to take. And over here, you can actually put weights on these plans, on these subcategories of plans. And depending upon the weights, you can choose which one to choose first and which one to choose next. The one with the highest weight factor could be the one you choose. And the weight could be a factor of time, it could be a factor of energy requirement, it could be anything. Is it clear what I just said? Hmm? Yes, I'm assuming it is clear. Okay, so now as part of hierarchical activities, you can also look at how to control values of variables. Control values of variables meaning whether you actually want something to be done or not, whether you want to include that particular variable within your plan, whether you want this thing that you see, it is possibly you want to include this variable, this is you want to delete that variable, and this is you are unsure whether you want to keep or delete that variable, keep or delete a parameter, keep or delete a choice. Okay, so over here what we see is given an action h1, you have a precondition of this. Okay, means not a, precondition of not a, effect is a, and you decide whether you want to delete b. Okay, so you keep a and you delete b. Similarly, action H2 is something else. So now if B is true in the initial state and your goal is A and C, then H1 and H2, how can they achieve the goal? Because you see, in the very first step, if I do H1, A is true. And in the second case, when I follow H2, when B becomes negative, this precondition is satisfied and then C comes. Because before C, I have kept that clause that it may be there, it may not be there. And A is definitely going to be there. So if I have a goal where A and C is my goal, the parameters A and C or the values A and C of variables is my goal, and I have an initial state of B which is true, then possibly if I follow sequences H1 and H2, I can achieve them. Did this make sense? Yes. Yeah, unless you say I won't know, I am assuming it is clear. Okay. So this is about hierarchical planning. Now I have a few more things to say. Yeah. So in hierarchical planning, the different components of hierarchical planning is one is the high level goals, the big picture of goals that you have to set for that particular operation to complete, the tasks which are the actions that you have to take, and the sub goals are the intermediate objectives. You decompose a certain high level goal into sequences of sub goals and tasks. A hierarchical structure is important because you move from higher, broader goals to intermediate sub goals to atomic primitive functions. Okay. Task dependencies and constraints are important. Why? Because if you do not look at task dependencies and constraints, you will not be able to decide which primitive action to do before what, or which sub goal to achieve before what, or if multiple sub goals can be achieved concurrently. Okay, so identifying task dependencies and constraints is an important factor when you are doing hierarchical planning. Then representation of the plan is very important. When you decide to draw the graph or the tree for the plan, then obviously you need to look at how these edges are going to connect with each other between the two nodes of states, what action you're going to take, what parameters, what values are going to be active, what are the preconditions, right? What is going to be the effect of that action? So all of that has to be charted out in the graph. And plan evaluation and optimization, meaning like you have a plan made. Say you have multiple such plans, just like I told you, you can look ahead and design multiple plan options. And now you can think and evaluate which one will take less time, which one takes more time, which one minimizes a cost function, which one maximizes a cost function. Depending on that, you can choose which one to take. And there is always the option of reflecting on what you have done. So while you are choosing which plan to take, you are deliberating on what to do. And when you have taken a certain action, and then you revisit it and you try to figure out if plan B would have been better, that is when you are reflecting. Okay, so through a hierarchical planning algorithm, you can actually move from deliberation to reflection. Okay, if you maintain a log of activities of which plan you took, at what time you took, what was the entire critical path that you chose between these actions, if you decide, then you can, during reflection phase, you can definitely backtrack and see where things may have gone wrong. If you make a constant log of at time t, activity, variable previous value, variable new value, where A is action and T is time. If you keep a rough log like this, then obviously you can keep backtracking and you can uh, revise options. If that option is available, you can revisit, you can revise. Okay, so hierarchical planning strategy is something that, in fact, all of us do when it comes to doing anything. Okay, any questions? Is it all making sense? So now what is the disadvantage of a hierarchical planning graph? Of a hierarchical planning strategy, what is a major disadvantage, and how do you think you can actually resolve that disadvantage? Or what kind of trade-off are you going to do to resolve that disadvantage? Anybody? Hmm? Don't you think actually decomposing a process and identifying sub goals, this could lead to a very large tree? The the complexity of the tree that could be generated, this hierarchical structure, the complexity could be very huge, both in terms of memory and computational requirements. Don't you think this tree could be very expensive?
Yes,
Yes.
ma'am.
Yeah. So if it becomes expensive, do you have any thoughts on how you could make a trade-off on how much you want the tree to grow, or how many levels or to what depth you want the tree to grow? Any trade-off you think you would like to, any strategy? Just think from real life what you do. See, one strategy is you design the whole tree and then you take a decision. Okay, you actually sit with pen and paper, you design the entire strategy from top to finish, and then you choose, and then you decide on the plan of action. Or you can make intermittent actions and choices. You take certain steps, and then again you plan, again you take certain steps, and again you plan. So now the first step, the first procedure, where is designing the entire tree and actually looking where, this is a brute force algorithm. This is very conservative in nature. Okay, but if you look at taking a certain action and then making a plan, you do a look ahead, you make a certain plan for, say, the next 6 steps, then you choose another activity, and again you make a plan. This is somewhat an optimistic design strategy. So here what you're doing is you are maybe compromising a little in terms of accuracy, in terms of looking at all possible options at the same time. Maybe you are not doing that kind of an approach, but here you are making it effective in the way that you are not hogging the entire memory space with every option. Okay, or everything. You are not making this entire tree very heavy. So what you're doing is you're taking an action, looking ahead, and again taking an action, and again looking ahead. So now how frequently you are going to shift between this action and planning phase, that is entirely upon your resource availability, depending upon your use case. If it is, for example, a scenario where you have a very uh, for example, a medical scenario, then it might be wise to actually look at all possible options and then take decisions. Okay, but if it is something about maybe talking about a robo vacuum cleaner, then possibly taking an action, then planning the next step, again taking an action, planning the next step, maybe something like that would be effective. Okay, so depending upon your use case, you can actually make trade-offs and move ahead. You need not design the entire hierarchical tree and then make a plan. Okay, so you can have bursts of activities and plans. And if you maintain a log, you can always come back and do your reflection activity phase. You can always do that. Hmm. Does that make sense?
Yeah, ma'am.
Yeah. Any questions? Okay. So now after hierarchical planning, what is very interesting is in the real world, we are dealing with sensorless data, maybe. You may not have enough sensors to collect all that information that you need. So you might have certain states which are occluded to you, or certain information which is not available to you. Okay, so you have to deal with situations where information is not available or they're partially observable. Not everything is available, but partially observable. Or you might have to replan. So over there, what is important is arriving at belief states. That is where your knowledge graph belief factors or your confidence factors are going to help you. How? Like, say for example, um, you have certain sensors which take into consideration only maybe say the flow of speech, okay, but they don't look at the expressions on the face. Hmm. So now, given only the voice, you arrive at a certain perception of what the person is feeling, and then you take an action based upon that. This is what happens when you're on a phone call. You can't see how expressive the person is in terms of facial expressions, Or say when you're looking at SMSs and WhatsApp messages, you are just looking at texts, but you don't know whether this is a sarcastic text, or whether this is incorrect, or whether the person is making fun, or whether the person is really meaning it. Okay, so you have a situation here where you have some information, but you don't have access to sensors that will lead you to the complete information. So then what you do is you act upon your own belief value. That belief being a function of previous interactions, right? That, say for example, you and your friend were talking about a topic T, then A sends a message and you receive it, but now you are confused how to treat that message. Okay, so you have different options whether to take it sarcastically, or whether to let it go, or whether to actually take it to your heart. You have different ways of dealing with that situation, right? Given topic T, A and B. So now you as B, how do you decide upon it? See, over here, what do we have is a situation where you do not have sufficient sensors to give you all the information. You just have a text, right? And that is just plain text with you don't know what emotions are embedded in that text. But how do you arrive at the emotions embedded in the text? As a function of past interactions. And this leads to belief values. If you know that the person has a sarcastic sense of humor, then you know what to do with that piece of information. If you know that the person never makes fun, or has a low key sense of humor, then you know what to do with that person. You know how to deal with that message. Okay, so this kind of a belief value that you have on the information that was exchanged, the belief value have that you have on the person with whom you are talking to, is going to affect the way you are going to plan and respond to that situation. So here it is not just about objective data where I say I have lost my glasses, find them for me. Okay, this is a very objective situation. Here you are not dealing with emotions, but here if you are trying to talk to a social AI agent, or a social AI agent is trying to talk to you, then this kind of sensorless information processing could become very important. This kind of sensorless information planning, you have to have that kind of a module in your system to be able to plan the kind of action required for this kind of activity. You might have a partially observable system. You get some data, you don't get some data. Okay, then what do you do? Similarly, you decide upon the percept schema. Percept schema meaning the perception values, the sensory information that you have. You plug them into a placeholder, activate your knowledge tree, see what belief values come up, and then accordingly you plan. So over here, your hierarchical planning tree is not just about activating objective processes, but also dealing with subjective information. Okay, so when you are planning, say when I'm planning to talk to you, or say a TA has done something wrong and I want to scold the person, I have to plan how to scold the person. Whether I'm just going to blast that person off, or I'm going to talk to that person in a calm way, in a more uh, understanding fashion, or whether I'm going to ask the person what happened, why he or she didn't do what was asked. Okay, so there is a lot of planning happening over here. And if I know how the person is, or say if I know that the TA is a very conscientious person, then I know how to deal with the person, isn't it? If I know that the person is not going through a good medical situation, I know how to deal with that person. So past histories and belief values also become a part of your planning algorithm. So all this while we were talking about goals and sub goals and activity plans and reach states, here you can also include parameters that incorporate these belief states as well. So preconditions, effects, all of this can include affective states also. Okay, so when it comes to planning in the real world, this is something that we can definitely talk about, or we can definitely think about. And replanning. Say, for example, you have a goal, sub goal, entire hierarchical tree drawn out for you, You took a course of action and it didn't turn out the way it was expected. So now here I have a question. This entire sequence of goals and activities or goals and states that we have designed, right? This entire sequence in a hierarchical plan, how do you think we arrive at this plan? What is the very first step of creating such a plan? If I give you an activity that you have never done before, how are you going to plan how to do it? Yes? One thing is being trained in it, right? One thing is you have a sufficiently strong knowledge base which knows how to map sensory patterns into activity patterns, sensory patterns into objects, and accordingly help you plan things, right? But if, for example, I give you an activity to do which you have never done before, how are you going to plan it? What essential step are you going to incorporate as part of your action plan? Yes, I just talked about it a few minutes ago. Don't you think including predictions would be a very good thing to do as part of the planning algorithm? Making predictions
Yes.
means like you have a certain state, you have you have certain state, you have activities, and you arrive at state S0. This is very deterministic. You know exactly what to do, and this is a function of, say, past experiences. Your knowledge base is entirely trained to identify one state, set of actions. This procedural memory that you have in sync with state S leads to action A and state S dash. But if you don't have that kind of information, then what you do is you start predicting. Right. You have sensory information. You look at similarity patterns. Maybe you use a clustering algorithm to see with what object the sensory information coincides with. Say it is a cat. Now, if you have a cat in hand, then what do you do? Okay, do you shoo it away? Do you keep the cat? Do you give it milk or give it fish? What do you do? Okay, so you make that decision based on a prediction that this is a cat. But now, when you have taken that step and you realize it's not a cat, it's something else, then you replan, right? So, this kind of making a prediction, taking an activity stance, arriving at a state, and then replanning given need. This is something also that real life planning or algorithms need to incorporate. Okay, so in a scenario, it need not be that you have information and knowledge of everything. So you have to incorporate prediction algorithms, clustering algorithms, learning algorithms, all of this as part of your planning strategy. Rather than the incorporate as part of your planning strategy, rather as a foundation of your planning strategy. That's the better way to put it. Okay, so you have all that you have learned about machine learning, deep learning, supervised, unsupervised reinforcement learning, all the different architectures that you have. All of that becomes available to you when you have a plan and you decide what to do about it. Okay, so you can look up patterns, you do pattern recognition, you identify which sectors or what object does this coincide with, and then accordingly, whatever procedural memory is activated, you take steps based on that. You create a hierarchical plan of this is what has to be done. So hierarchical plan can be essentially a function of a procedural memory given a certain state. Right? For that particular state, what process can you do to move to state S dash or some goal state? Right? So this entire procedural memory can be activated given your knowledge base. Okay, so now you can. append your knowledge base given new experiences that you have gathered. You took a plan, you made a plan, you acted upon it, you learned something new. So you can append it to your knowledge base. So, this entire system where you are learning, acting, predicting, all of this becomes a part of any real world AI system. Not only AI, any real world intelligent agent. We are all doing it. Human beings are doing it, animals are doing it, even trees are doing it. Have you read any papers where trees do a lot of communication and trees do a lot of cognitive activities? Any of you read that? Read those papers?
No, no.
It's actually very interesting. You must. Trees have wonderful cognitive functions happening within themselves. The only thing is their time scale is different. While our time scale is within maybe 3 or 4 seconds, their time scale could be months. Okay, that's the only difference. Otherwise, trees are essentially very cognitive creatures, cognitive agents. Trees too. Okay, so animals are also doing a lot of planning. We are doing a lot of planning. So if you're trying to design an intelligent agent that has to work in a world where all of us are functioning, then obviously you have to think about these kinds of processes. Okay, so hmm. So now, when we are talking about learning as far as the foundation of a plan, what are the different things that we need to incorporate in our learning strategies is direct mapping. First thing is direct mapping from conditions onto the current state. Conditions meaning you have a sensory packet, you do uh, some kind of recognition algorithm, you execute upon it, and you identify object which leads to maybe state S1, which is identification of the object. Okay, so now at S1, you have this sensory information available to you. So now given this S1, you can think about action A1 or action A2 or action A3. This is where your procedural memory has come up. So now here what you can do is maybe give more attention, acquire more sensory information, let that object go, ignore that object, or go hands on to process that object. Okay, so this direct mapping from sensory conditions onto the current stage to lead to actions. Okay, so this part of creating a procedural memory as part of your knowledge base is going to be very important. Either you can hard code it or you can make it adaptive in nature, where you learn new rules. Remember the other day we were talking about having a very huge rule base for any use case. So you can start with a very effective hardwired rule base, and then you acquire new rules as part of your system. And the moment you start acquiring new rules, what becomes important is indexing these rules. What kind of indexes are you going to use so that the retrieval is very fast? What kind of keywords, what kind of metadata are you going to use in your data structures so that the retrieval is very fast? Retrieval of procedural memories is going to be fast. So when you're implementing this into your system, you have to think about keywords or metadata that you're going to use to activate procedures. Right, like I said, this is a cat. So then procedural memory of all cat activities come up. And then you decide what has to be done. Right. So this this thing of actually appending your knowledge base with new rules, starting with a hardwired rule, is possibly an effective mechanism to incorporate in a real world system and particularly in an embodied AI system. Okay, then you need to have algorithms to infer relevance, meaning in the hierarchical tree, you can have a brute force approach where you design the entire tree and then you make a decision. Or you can just pick up certain facts, or you just pick up the steps that are important, or you give weights. you identify which sections of this hierarchical tree are important. Okay, so you have to have mechanisms to identify relevance. So here relevance could be based upon sensory stimuli, it could be based upon pattern recognition with existing knowledge. Okay, so there are different ways in which you can identify relevance. Then we need to know how the world evolves. The world evolves meaning uh, one is a world in which, say, you're trying to design a vacuum cleaner and furniture moves. So the world changes, the perspective of the world changes. And when we are dealing with a social system, human beings' feelings, facts, thoughts, ideas, they keep changing. So if you want to design an intelligent agent as a friend or an aid or say a psychological aid, then it possibly needs to identify changing thinking patterns in human beings also. So this is not just a regular chatbot. Okay, it is actually identifying that today you had this particular perspective to one thought, but tomorrow it is changing. So in between some learning has happened. In between some reflection has happened. So this uh, actually I respecting this or identifying that there is a change in perspective is very important when it comes to designing a real world agent or real world AI agent. Doesn't this often happen to us? Like we see a person doing something which is unpredictable, and then we say, this is not you. You never do something like this. Then the person says, no, I just tried it. So then you respect that, isn't it? So for a social AI agent that is going to be, that is going to act in a social world, it needs also to identify that there has been a change in perspective. Okay, similarly, changing in furniture, these are objective in nature. Okay, so you can have objective as well as subjective information to deal with. Then, obviously, information about results and actions. This is a very integral part of any procedural memory activity. Utility information is also important. Utility information meaning you take an action. What are the outcomes? What are the goals? Has it increased, maximized any cost function? Has it minimized the cost function? Has it depleted you of energy? Has it made you more excited? What has it actually resulted in? So identifying utility functions to gauge whether an action has been effectively done or not, that is also important. Okay, so these are certain things that when it comes to designing a real world situation, it is very important. And this is pretty much all that I wanted to talk to you about. And yes, any questions, any thoughts, algorithms, design strategies, anything? So you mean to say everything is clear? Okay, so now when it comes to representation of knowledge and information, you can use propositional statements like first order logic statements. You can use Bayesian networks to show prior knowledge and effective decisions. After that, you can draw decision trees. You can do anything. Okay, so now I'll talk a little about multi-agent planning also. Why multi-agent planning? Because say we are trying to, in the real world, it's not only about solo activity. You might have to interact with other agents also. So when it comes to interacting with other agents, it could be loosely coupled or tightly coupled. Right? Loosely coupled meaning that it's not necessary that you share the same knowledge base, okay, or you share the same resources. It is just like um, one person reacting with in sync with another person, or one agent acting in sync with another agent. Okay, but in tightly coupled system is you have the same knowledge base, you have the same environment, you have everything the same, but you just have two agents working in that situation. Okay, so given the kind of scenario, you can have tightly coupled agents or loosely coupled agents. Then you might need to do multi-body planning. Multi-body planning meaning you have two agents that are, say, loosely coupled. Then you have to take decisions that are in sync or coordinated activities or synchronized activities between these two. Say, for example, you're designing two agents that are trying to play a game of tennis, right? So, what are the different kinds of activities or what kind of joint action plans that you need to design over here? Hmm? You have two agents.
Making service like
Hmm.
services. Uh,
Making service, that is the broader goal. What are the sub goals?
sub goals should be ready for the ball or
Hmm.
signal, uh, like
Hmm.
ready with the position.
Hmm. Identifying the position of the ball, identifying whether the ball at all is coming towards the person or not,
Yeah.
right? Towards the agent or not. Then muscle movement, movement of the joints, right? Those are primitive options. Movement of the joints, movement of the hand. Those are primitive options. But things like actually identifying the position, the coordinates of the ball, the approximate velocity with which the ball is arriving or approaching. Okay, and then it cannot be like you hit the ball in one direction and the other agent is looking in the other direction, right? So there has to be some amount of synchronicity over here. So here you can design rules that actually preconditions that actually make that point clear that these two agents are interacting with each other. Okay, so these kinds of joint plans need to be made, can be made when it comes to multi-agent systems. And again, when you are dealing with social systems, then actually embedding social laws makes sense, because if you try to embed social laws within an AI system, you are actually taking it to the higher levels of contemplation like self reflection and self consciousness. Here, talking about the term consciousness is not, um, it's rather debatable because we still don't have a mathematical definition for consciousness. But there's a lot of work happening in consciousness in the philosophical world, and there are some AI researchers also who are trying to define what consciousness is, and if we can actually embed it in an AI agent. There is a lot of work happening in that direction. That is separate, but at least self-reflection can be done, right? Reflection to self-reflection, how does it differ? Self-reflection is when you start thinking about how to improve on what you already know. How to ask someone or how to ask another agent how you can do something. Or you identify something is good in someone and you want to figure out how that person does it or how that agent does it. Okay, so if you have a social mechanism coming over here, you know how to ask the right questions, you know what questions to ask, then possibly you have a social interaction happening and scope for self reflection. So you remember that on the first day I had shown the green robot and the pink robot scenario? So there was a lot of self reflection happening over there, if you remember. Right. One agent was trying to help the other agent, and then they said thank you, and then the one that helped said, okay, I collected some brownie points for the day. Right. So here there is a social law coming in that when there is another agent in need, you help that person. So now here I want to talk a little about biases. Do you think we are all biased or are we unbiased? What are your thoughts on that? Because when
Yeah,
it
definitely we are biased with some information.
hmm, this is a fact. All of us are biased. But now the question is whether it's a good bias or a bad bias. That is the fundamental question. So when we have data, it is going to be biased in some form or the other because it is not possible to collect all perspectives of everybody in the world. It's not possible to do that. And whenever you design a survey to collect facts from experts, invariably you are creating a closed environment within which you're asking the expert to react. A closed environment need not represent what the real world is. Just like if I take EEG readings in a lab, I am not subjecting you to the real world. So I exactly don't know what EEG signals are happening. But I'm putting you in the lab, giving a hypothetical situation for you to react to, and I'm taking EEG signals. So definitely this data is also biased. When it comes to collecting survey information, when it's coming to collect expert information, they're all biased in the sense because it is a function of what that expert already knows or what belief values that expert already has. So now the question over here for all our AI agents is identifying what is good and what is bad. When I say I am biased towards equality and equity, I am biased, but it's a good bias, isn't it? So having this bias is good, isn't it? Being biased towards equality and equity. It's a good bias. So now how do we model goodness? That is the question. And that is something that researchers are now looking after or looking into. What do we define as good? And this is a very socio-cultural answer because what is good in one culture may not be looked upon as good in another culture. One culture could be materialistic, while another could be more spiritual, right? So, if I have to incorporate these kinds of differences within my bias modeling, that's very interesting, isn't it? So, these are certain open questions that are there and they are all glaring at us. And why these questions have come is because we are introspecting on how we deal with the real world, how we plan in the real world, how we act in the real world. Since we are introspecting on this, that is why these questions are also coming up in the AI world because we want an AGI agent, we want an artificial, generally intelligent agent, right? Something, an agent that is able to generalize across all knowledge forms, is able to identify what is bad and what is good. So, for that, we need to know what is good and bad. We need a mathematical definition for it. Or again, we have to collect surveys and then attach belief values to information. The positive value, negative value, right? But even if you collect information from experts and you put quantities, do you think it actually models goodness? Does it model fairness? What do you think?
So, what was the question, ma'am?
My
Fairness.
question was like, I have a certain data set and I want to know whether it is biased towards it has a good bias embedded in it or a bad bias embedded in it. Okay, so one way to deal with it is I present the data to experts and I collect their survey values and then I do statistical analysis to identify whether it is tending towards good or bad.
Correct.
Right? That is a very objective way of handling that particular problem. But does that actually model goodness?
So, see, model goodness will depend on the rules and all those things, right? The data
Hmm.
which we are. let's say, see, whatever the data, statistical data we are getting from the expert,
Hmm.
those are based on some rules. Like Penny says, okay, this is the point, this is the sub point. Those are based
Hmm.
on the rules, right?
Hmm.
So if those are expert coming from experts, so it is fairness, right? For
Could
modern
be.
education.
It could be. It could be. But what I mean to say is, uh, an agent helping another agent. Okay, it's not just about data,
Mm-hmm.
right? It's more about the activity of helping, this notion of helping. Remember, I talked to you about qualia, right? The essence of helping, the essence of goodness, that is not captured when we are trying to model anything with data and expert values.
Correct.
That qualia is missing in our models. So now the debate when it comes to philosophy and AI is, do we need to model qualia or not? When it comes to planning, do we need to incorporate qualia as one of the parameters of our planning algorithms or not?
We should, right?
It should be.
Yeah.
It should be if you're dealing with a social system, if it is an objective system, right, like a vacuum cleaner or a drone or an autonomous vehicle, then possibly qualia is not important. But if you're dealing with a socially embodied system where you are trying to deal with a social agent, then maybe having a sense of a qualia of goodness, fairness, trustworthiness is good.
Also, remember, if let's say this other the objective systems like drone,
Hmm.
those are also is dependent on the other agent. So
Hmm.
then this will be required, right?
It could be required depending upon the use case. If it's like a delivery drone, then it doesn't need to. But if these drones are interacting with each other towards a bigger objective,
Okay.
then maybe. Hmm. So these are some like open research challenges in the modern AI world. These are some challenges. So while deep learning, generative AI, they are giving us an illusion of um, of a lot happening. They're giving us an illusion of a lot of learning happening, of a lot of pattern recognition happening, right? A lot of embodiment happening. But in terms, but when we look at it from a philosophical perspective, we are lacking in some factors, right? We are all very, very data driven. Whatever architectures we have at the moment are very data driven, are very heavily dependent upon training.
Mhm.
Hmm, right. So, yeah, eventually, maybe we can always hope that we will gain more insights from biology and neurosciences, and maybe we'll be able to take it forward. Okay, so this is pretty much, yeah, yeah. Question?
No.
No. So this is pretty much all that I had in mind that I wanted to discuss. And this is pretty much all that the syllabus talks about. So for the major exam, from fractal 1 and 2, there are two questions. Okay, it's roughly 20 marks. 10 questions for question 1, 10 marks for question 1, 10 marks for question 2. And question 3 is going to be from fractal 3, which is about I have given you a very specific situation for which you have to design an agent. Okay, you have to talk about ontology, what kind of mapping objects rules, what kind of planning algorithms. Now, here it doesn't have to be exhaustive, not necessarily that you have to consider all possible scenarios in the world. You have limited time. You can think as much as you can. Okay, so you can use propositional statements, you can use Bayesian networks, you can use decision networks, you can use knowledge graphs, you can use belief values, you can use anything to model. So it is a very specific problem for which you have to work. And I have
And what is the
10.
weightage of question 3, ma'am?
The weightage of question 3 at the moment I've kept it as 40, but I think I will reduce it to 30. Okay. Means questions will remain the same. I'll just reduce the points for every question. Yeah.
And ma'am, how much time you will get, because in minor one, the
Then this is 3 hours,
this
3 hour
is
exam.
okay, okay,
Yeah,
okay.
yeah. Major exam is for 3 hours. Hmm. So roughly that's the plan. So 14th is your exam, and 15th we have to release the scores on ERP. You will get to see your scores on the 16th or the 17th. Okay, but before that, the major scores, you have access to your minor scores.
Yes.
Yes.
Yes, ma'am.
Quizzes and minors are all done, right?
Yes.
So assignment scores, I will release them either tomorrow or day after. Okay, we have started the evaluation procedure. So either tomorrow or day after, the assignment scores will be released, and major scores you will get to see them, the major grades you will get to see them on the 16th or the 17th, but major scores I intend to release by end of day 15th. Okay, that is something that we have to do. So possibly 15th late evening, maybe I will put up the scores in Google Classroom for all of you to go through and see and get back to us if you have any problems, so that we can finish everything by 15th end of day. We have a very tight deadline this time. Hmm. So be very, very precise in your answers. Be very specific. The questions that I have that has been asked in the major, there is no scope for any objective information, any subjective information in it. You can be as objective as you can in the model. You don't have to deal with any subjective information. Okay. So, hmm, it's very specific. So you can draw diagrams, you can draw rules, you can write rules, create your own rule base, knowledge graphs, ontology graphs. You can do anything, but just make it precise. And if you have made any assumptions as part of your design, you have to write that very clearly. Any assumptions, you are allowed to make reasonable assumptions as part of your work. Okay, you might assume that your robot is going to have 6 legs. So write that clearly. My robot has 6 legs, each leg has one function, which is so and so. So write that clearly. Okay, so assumptions need to be made very clearly, and answers need to be very precise as you can be. Don't write a lot. Okay, just be precise in your thoughts, very direct questions, and please make use of diagrams to substantiate your answers. Okay, feel free to draw to substantiate your answers and be neat in your work. Okay, this is something that I wanted to tell you. Any questions?
So last question, like assignment we did, right? Yeah.
The assignment was elaborate. This is not that elaborate.
Oh,
Mhm. This is very objective. Like I said, you're not dealing with any subjective information over here. You are allowed to incorporate subjective information, but it is not necessary. You need not. If you want, you can. Hmm, okay. Any other question? All groups have submitted their work, right?
Yes.
Hmm.
Yes, ma'am.
Mhm. Good job. Take care then. So I think we can end the classes here, and all the best for your exams. all the best for whatever the future has in store for you, and keep doing well. Okay.
Yes. Thank you, ma'am.
Thank you, man.
Thank you, ma'am.
Thank you, thank you. How many marks are allotted for major? 40 to 50 marks. 40 marks to 50 marks questions, not more than that. Hmm. Like I said, I had initially given for question 3, which is for fractal 3, I had given around 40 marks. I think I'll reduce it to 30.
Ma'am, overall, what is the weightage of major? It's 70.
40%. 40%.
Okay, 40%.
Yeah, that is the institute rule.
Okay.
Yeah, 60% is the rest and 40% is major. Okay, so then we can stop here.